Assalamu alaikum, brothers and sisters. Welcome to the journey of quest where we quench your thirst of knowledge. Have you ever paused to wonder where it all began? How did this vast universe come to be, and what secrets does the origin of Earth hold within its cosmic history? In the grand tapestry of the cosmos, our Earth is but a speck, yet its formation is a tale as old as time itself, woven with theories and mysteries that challenge even the brightest minds. In our cosmic journey to understand the origins of our solar system, let's delve deeper into the Nebular Hypothesis. Imagine a colossal cloud of gas and dust suspended in the void of space. This is not just any cloud, but a molecular cloud, vast and rich with hydrogen and helium, the simplest and most abundant elements in the universe. As we zoom into this nebula, through detailed animations, observe how the cloud begins to experience gravitational disturbances. Perhaps triggered by the shock wave of a nearby supernova, the cloud starts to collapse under its own immense gravity. This collapse is not uniform. Instead, it creates a spinning motion, much like a figure skater pulling in their arms to spin faster. Visualize this process through our animation. The cloud spins increasingly rapidly as it contracts, causing the material to flatten into a disk. This is the protoplanetary disk, and at its heart the material is so dense and under such tremendous pressure that it begins to heat up dramatically. Now focus on the center of this disk. Here, in this seething furnace, a protostar, our future sun, begins to form. The animations show how over millions of years, the temperature and pressure at the core of this protostar becomes sufficient to start nuclear fusion, marking the birth of the sun. But what of the material not consumed by the formation of the star? Surrounding the newborn sun, the remaining dust and gas continue to orbit. Over time, these materials collide and stick together, forming larger and larger clumps, from dust grains to pebbles, and eventually to planetesimals. These are the building blocks of the planets. Through our detailed visualizations, watch as these planetesimals gather more material, growing into the familiar planets of our solar system. Each animation not only captures the dynamic and chaotic nature of this process, but also highlights how from a simple cloud of gas and dust, an entire solar system can emerge, illustrating the beauty and complexity of the Nebular Hypothesis. As we continue to unravel the mysteries of our solar system's birth through the Nebular Hypothesis, let's focus on a pivotal event: the formation and ignition of the Sun. Picture the protoplanetary disk we discussed, a swirling mass of gas and dust with a dense center. This center, where our Sun is beginning to take shape, is not just a random assembly of materials, but a crucible for the complex processes that lead to the birth of a star. As the gravity pulls more and more material towards this central region, the density and pressure increase exponentially. Visualize through our animations the particles colliding and fusing together, generating intense heat. This heat is not ordinary. It reaches millions of degrees Celsius, temperatures so extreme that hydrogen atoms begin to lose their electrons, creating a state of matter known as plasma. Now enter the critical phase of nuclear fusion. Our animations slow down to show hydrogen nuclei in this high-pressure, high-temperature environment, overcoming their natural repulsion for each other and fusing to form helium. This process releases a tremendous amount of energy in the form of light and heat. It is this energy that halts the further collapse of the material and leads to a stable equilibrium where the outward pressure from nuclear fusion balances the immense gravitational pull. Thus, our Sun was born, a glowing sphere of plasma, radiating energy across the solar system. This energy not only supports life on Earth, but also played a crucial role in the further evolution of the solar system. As we proceed, our animations highlight the continuous fusion process that powers the Sun and influences every object within its reach, setting the stage for the formation of planets and other celestial bodies. Transitioning from the fiery birth of our Sun, let us now explore the next monumental chapter in the cosmic story of our solar system, the birth of the planets. As the Sun ignited, shedding light and heat throughout the protoplanetary disk, remnants of gas and dust that weren't swept into the Sun began a fascinating process of their own. This scene unfolds with our detailed animations, illustrating how these materials started to coalesce. Imagine countless particles floating in the disk around the newly formed Sun, each piece colliding and sticking together through a process known as accretion. These early interactions were gentle, almost like a delicate dance in the cosmos, gradually forming larger and larger clumps of material. Our animations zoom in to show how these clumps, or planetesimals, grow over time. As they become more massive, their gravitational pull strengthens, attracting even more material. Watch as these growing bodies sweep through their orbital paths, clearing lanes in the disk. This process, depicted through dynamic visual effects, highlights how the gravitational forces and collisions sculpted them into spherical shapes, eventually forming the protoplanets. These young planets continue to collide and merge, creating the diverse planetary bodies we are familiar with in our solar system today. Through this detailed visualization, we grasp not only the chaos but also the structured beauty of planetary formation, a direct consequence of the materials and forces left in the wake of the Sun's dramatic ignition. As we proceed to the next scene, keep in mind this intricate ballet of particles, a dance that shaped worlds from dust and gas. As we delve deeper into the mysteries of our solar system's formation, let's focus on a pivotal stage in the planetesimal hypothesis. This theory provides a fascinating glimpse into how the planets may have started as mere grains of dust. Picture the young solar system as a vast disk filled with gas and dust spinning silently in space. This scene beautifully illustrates, through crisp animations, the initial conditions where countless tiny particles floated within the nebular disk. These particles, no larger than specks of dust, began to interact under the subtle but persistent forces of electrostatic charges and gravity. Our visuals zoom in on these minute particles as they collide and stick together, forming larger aggregates. This process, known as accretion, is elegantly depicted with particles gradually building up to form what are known as planetesimals, the building blocks of planets. Imagine these growing clusters ranging from a few centimeters to several kilometers in diameter as they continue to attract more and more material. The animation highlights how these early planetesimals are not yet planets, but are crucial in the planetary formation process. They provide the core mass needed for the gravitational pull to become significant, drawing in more debris from their surroundings. This scene not only enhances our understanding of the initial stages of planet formation, but also sets the stage for the complex interactions that lead to the birth of the planets we are familiar with today. As we transition to the next scene, keep in mind the monumental journey these tiny particles undergo, from dust to planetesimals, paving the path toward becoming full-fledged planets. In the grand narrative of our solar system's formation, the transition from planetesimals to full-fledged planets is a spectacle of cosmic proportions. As we left off, small planetesimals had formed, ranging from a few centimeters to several kilometers in diameter. Now let's explore how these planetesimals began to accrete more material, setting them on a path to becoming the planets we recognize today. Imagine our solar system as a bustling construction site in space, where each planetesimal competes to gather material from the surrounding nebula. The animations show the chaotic environment of the early solar system, with countless collisions and interactions. As these planetesimals orbit the young Sun, their gravitational influence slowly increases. Visuals illustrate how, through gravity, a planetesimal attracts smaller particles and other planetesimals towards it. This process of accretion is gradual but relentless. As the planetesimals grow larger, their gravitational pull becomes stronger, pulling in dust, gas, and debris from their orbits. The visuals zoom in on a particularly large planetesimal, demonstrating how its increased gravity creates an impact zone, where smaller objects collide and merge with it. This accumulation of mass isn't just a matter of size, but also increases the heat and density at the core of the growing planetary body. The scene transitions to a dramatic animation depicting a series of significant impacts. Each collision contributes more material and energy, compacting the planetesimal further. Over millions of years, these growing bodies undergo differentiation, a process where their internal structures begin to organize. Heavier materials sink towards the center, forming a metallic core, while lighter materials form the mantle and crust. As the narrative progresses, the scene emphasizes that this growth phase is not only about accumulating mass, but also about surviving numerous collisions that can either lead to growth or destruction. The animation slows to focus on a pivotal moment, the transformation from a chaotic collection of planetesimals to a mature planetary body with a defined structure. By the end of this scene, viewers will have witnessed the awe-inspiring journey of planetesimals as they evolve into the complex layered planets that orbit our Sun today. This crucial stage in planetary formation not only shapes the physical characteristics of the planets, but also sets the stage for the next chapter in the cosmic saga of our solar system. In the intricate ballet of cosmic evolution, the stellar accretion theory provides a fascinating insight into the birth of new stars, a process pivotal to the development of our universe. As we delve into this phenomenon, visualize a vast swirling cloud of dust and gas in the galaxy. This cloud, known as a molecular cloud or stellar nursery, is the cradle of star formation. The scene begins with an animation of a dark, dense molecular cloud. Slowly, disturbances within the cloud, perhaps from the shockwaves of a nearby supernova or the gravitational pull of passing stars, begin to create ripples. These ripples increase the density in certain regions of the cloud, leading to the formation of a protostar, the embryo of a new star. As the protostar forms, our visuals shift to show the accretion process in greater detail. The protostar, due to its gravitational pull, attracts more and more of the surrounding dust and gas. This material spirals inwards, forming what is known as an accretion disk. The animation highlights this disk, showing it rotating and funneling material towards the protostar at its center. The voiceover explains how, as the material falls onto the protostar, it heats up, increasing the temperature of the protostar. This process is visually represented by increasingly bright and intense colors at the core of the accretion disk. The heat and pressure continue to mount until the core reaches a critical point where nuclear fusion begins. At this moment, the protostar transitions into a main sequence star, shining brightly as a new sun. The scene emphasizes that this process of stellar accretion and star formation is not only a spectacle of nature, but also a fundamental process that leads to the creation of solar systems like our own. As the new star ignites, the remaining material in the accretion disk may eventually form planets, asteroids, and other celestial bodies. To conclude, the animation zooms out to show the newly formed star in the context of its galaxy. A single bright point among billions, each with its own potential to host life-sustaining planets. This stellar genesis from dust to a shining star underscores the continuous and dynamic nature of our universe. As we journey deeper into the cosmos, let's visualize the captivating sequence of events that leads to the formation of a star and the subsequent creation of a planetary system, as described by the stellar accretion theory. Picture a vast cold expanse of a molecular cloud floating silently in space. This cloud, dense and rich in gas and dust, is the stage for one of the most spectacular shows in the universe. Imagine within this cloud a disturbance, a wave of energy, perhaps from a distant supernova. This disturbance triggers a gravitational collapse in part of the cloud. As this region contracts, it gathers more and more material, forming a dense core called a protostar. Surrounding this protostar, visualize a swirling accretion disk composed of gas, dust, and debris spiraling gracefully under the newborn star's gravitational influence. Now focus on the protostar at the center of this disk. It continues to pull in material, growing hotter and denser. As the voiceover guides you, see the protostar reach critical temperatures where nuclear fusion ignites. Brilliant light bursts forth as a star is born, casting a radiant glow over the accretion disk. The scene shifts to show how not all material is consumed by the star's fiery birth. What remains in the spinning disk begins a new process. Smaller clumps of dust and gas start to collide and stick together, gradually forming larger bodies. These are the planetesimals, the building blocks of future planets. Visuals transition smoothly to depict these planetesimals as they continue to collide and merge, growing into protoplanets and eventually full-fledged planets. This entire process From the collapse of a molecular cloud to the birth of a star and the formation of a planetary system is a mesmerizing dance of cosmic forces and materials. To conclude, the animation pulls back to show the newly formed star, now surrounded by its own orbiting planets, a miniature solar system in the making. This breathtaking view highlights the incredible journey from dust to a structured, star-centered system, emphasizing the profound and elegant mechanisms of the stellar accretion theory. In the grand narrative of cosmic creation, there exists a theory as dramatic as any celestial event, the giant impact hypothesis. This theory proposes a colossal collision that shaped the very destiny of our planet and led to the formation of our moon. Visualize billions of years ago, a time when the Earth was young, teeming with volcanic activity and a hostile atmosphere. Now enter Theia, a Mars-sized body born from the same solar nebula that created Earth. As we delve into this animation, watch as Theia, drawn irresistibly by Earth's gravitational pull, hurtles through the cosmos on a collision course. The impact, unimaginable in its force, is a spectacle of raw cosmic power. Visualize the moment of impact. Theia and part of Earth's crust vaporize instantaneously, ejecting a massive cloud of debris into orbit around Earth. This cloud, composed of rock and molten material, begins to coalesce under its own gravity, forming a ring. Over time, this ring gathers together, birthed from chaos, to form what will eventually be our moon. This dramatic event not only gave rise to our natural satellite, but also contributed to the axial tilt of Earth, leading to the seasons as we experience them today. This animation not only captures the violence of this colossal impact, but also highlights the beauty of its consequential formation, illustrating the profound and often cataclysmic processes that shape our universe. As the scene fades, reflect on this monumental event, a testament to the dynamic and ever-changing nature of our cosmos. In the wake of the colossal impact between Earth and Theia, the cosmos bore witness to a spectacular and chaotic transformation. As the debris from the collision settled into a swirling ring around Earth, let's zoom in on this tumultuous phase of planetary evolution. Imagine a dense, swirling cloud of rock, dust and vapor orbiting our planet, a direct result of the cosmic violence that had just transpired. This ring, a temporary fixture in Earth's celestial journey, is the cradle from which the moon will emerge. As we visualize this ring through detailed animations, observe how particles within the debris begin to collide and merge under the influence of gravity. These aren't gentle mergers, but rather intense, high-energy impacts that gradually lead to the formation of larger clumps of material. Over time, these clumps grow larger, slowly starting to dominate the ring, attracting smaller debris towards them in an ever-increasing pace. This process, known as accretion, is crucial in celestial formation. The animation highlights how, over hundreds of millions of years, the majority of the debris consolidates to form the moon. This newborn satellite is not yet the smooth, spherical body we recognize today. As we witness the aftermath of the giant impact, and before delving deeper into the Nebular Hypothesis, let's pause to appreciate the intricate tapestry of theories that enrich our understanding of the universe's formation. Theories in astronomy, like threads in a tapestry, weave together to form a picture more complex and more beautiful than any single thread could illustrate alone. Consider the variety of scientific theories that play pivotal roles in explaining the phenomena we observe. Each theory, from the giant impact hypothesis to the Nebular Hypothesis, offers unique insights into the cosmic ballet that shapes planets, stars and galaxies. These theories are not competitors, rather they are collaborators, each contributing a piece to the puzzle of our universe. The Nebular Hypothesis explains the broad strokes of solar system formation, yet it is the detailed narratives like the Giant Impact Hypothesis that fill in the gaps, explaining specific events like the birth of our moon. Meanwhile, the Planetesimal Hypothesis and the Stellar Accretion Theory address the incremental buildup of celestial bodies from dust to planets. This diversity in scientific thought highlights not just the complexity of the universe, but also the dynamic nature of science, where multiple perspectives coalesce to deepen our understanding. As we explore these theories, remember that our current knowledge is the result of centuries of observation, calculation, and, most importantly, imagination. So, as we move forward, let us keep in mind the vastness not only of the universe but also of the human intellect and its capacity to explore the uncharted through science. Each theory, a beacon of knowledge, lights our way through the dark expanses of space, guiding us to a better understanding of our cosmic origins. As we explore the intricate theories that describe the formation of the universe, it's crucial to recognize that our universe is not a static entity but a dynamic, ever-evolving tapestry of matter and energy. Theories like the Nebular Hypothesis, the Giant Impact Hypothesis, and others provide snapshots of this grand evolution. Yet the universe itself does not cease to change and develop beyond these models. Astronomical observations show us that galaxies rotate and move away from each other. Stars are born and die in spectacular supernovas, and black holes bend the fabric of space-time, continuously reshaping the cosmos. This constant transformation challenges and refines our scientific theories, pushing the boundaries of what we know and how we understand it. Each theory adapts and evolves as new data emerges, mirroring the evolutionary nature of the universe it seeks to explain. Thus, as we delve further into the specifics of these theories, let us remember that they are not just static explanations, but living, adapting entities crafted by human ingenuity to decode the ongoing symphony of cosmic changes. As we traverse from the grand scale of an evolving universe to the specific mechanisms that shaped our solar system, it becomes evident how interconnected these cosmic phenomena are. Our journey through space is not just about understanding distant stars and mysterious black holes. It's also about comprehending our own origins and the delicate balance of conditions that allowed life to flourish on Earth. The theories discussed, from the Nebular Hypothesis to the Giant Impact Hypothesis, do more than fill chapters in textbooks. They illuminate the paths that led to our existence and could guide future generations as they reach for the stars. As we stand on this pale blue dot, our knowledge of the cosmos not only enriches our understanding of the universe, but also fosters a deeper appreciation for the planet we call home. By delving into these theories, we equip ourselves with the wisdom to navigate future challenges, ensuring that as we explore further into the cosmos, we remain mindful of our responsibilities to our planet and to each other in this vast universe. In the next scene, we revisit the Nebular Hypothesis, grounding our discussion in the familiar yet ever-compelling story of our solar system's birth. One of the prevailing theories is the Nebular Hypothesis, which suggests that the solar system was formed from the gravitational collapse of a giant molecular cloud, the nebula. This massive cloud, primarily made of hydrogen and helium, began to collapse under its own gravity, spinning as it shrank, forming a flattened disk with a hot, dense center. This center eventually ignited to form the Sun, while the remaining material in the disk coalesced to form the planets. Another intriguing theory is the planetesimal hypothesis. This theory builds on the Nebular Hypothesis but focuses more on the formation of the planets themselves. It proposes that small solid particles in the nebula disk stuck together when they collided, gradually building up into larger bodies known as planetesimals. Over millions of years, these planetesimals accreted more and more material, eventually forming the planets we know today. The theory of stellar accretion offers a slightly different take. It suggests that Earth and other planetary bodies formed from the accretion of dust and gas around a new star. As the star forms from a collapsing cloud of interstellar medium, it leaves behind a disk of material. Through a process of accretion, this material gradually builds up to form planets. Then there's the Giant Impact Hypothesis, particularly fascinating when discussing the origin of the Moon, which in turn relates to Earth's formation. This hypothesis suggests that a Mars-sized body, often referred to as Theia, collided with the early Earth. The impact was so colossal that a significant amount of debris was ejected into orbit around Earth, which eventually coalesced to form the Moon. Each of these theories provides a unique perspective on the formation of Earth and other planetary bodies. They highlight the complexity and dynamism of the universe, a place where chaos and order coexist in the dance of celestial mechanics. While these theories differ in details, they all underscore a fundamental truth about our universe. It is a place of constant change and evolution. Understanding the origins of Earth not only satisfies human curiosity, but also enhances our knowledge of other planets and the potential for life beyond our own. In wrapping up, the journey through these theories is a reminder of our place in the universe. It connects us to the past, informs the present, and inspires the future as we continue to explore the great unknown. So, as we gaze up at the stars, we do not just see the light. We see the echoes of the beginning, a beginning that holds the story of everything. Thanks for watching us share our videos, subscribe our YouTube channel, and press the bell icon, and stay curious for new uploads.